Factoring polynomials. There's a lot of techniques for factoring polynomials, and we learn those in Algebra 1. We continue them into Algebra 2 and pre-calculus. The reverse FOIL is a very popular strategy. And remember, FOIL, first, outside, inside, last, is used when multiplying two binomials. So we use the reverse FOIL when we have a trinomial and we want to factor it into two binomials. And so we start with two sets of open parentheses and we say what times what equals x squared, and we go x times x. What times what equals 6, but that also adds together to equal -5, and we get -3 times -2. Now, for some people this is easy. For other people, they want a strategy that works every time without having to think too hard, and the reverse box works great. Let's do the same exact problem. We put our x squared in the top left box and the +6 in the bottom right. Now we multiply these two together and we get 6x squared. And then we think, what are the factors of 6x squared that would also add together to equal -5x? And immediately I come up with -3x and -2x, and I put those along the diagonal. And now you want to remember the way the box works. Along the top, you can factor a common factor out, and there's going to be an x that I can take out. And then I ask myself the question, x times what is x squared? X times what is -3x? And now that top x times what is -2x? Now let's just check that the two constant terms multiply together to equal 6, and they do. So here I've factored it using reverse box. So it's one of my favorites, and we're going to use that later on in the video too. Here's the review of a couple of key formulas. Difference of perfect squares, remember? It factors into a minus b times a plus b. And then we have our perfect square trinomial. We can have a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. It's not very necessary to memorize those because you can just use the box. And another beautiful thing about the box is that we can use it by factoring by grouping, because that always seems to trip people up. There is a formula for the sum of perfect cubes and the difference of perfect cubes. I guess I'm starting with the difference of perfect cubes here. So when you have two perfect cubes that are being subtracted, I always remember you take the cube root of both first and last term and keep your minus. And then it's a squared. Now change the sign, plus ab plus b squared. For the sum of perfect cubes, it's the reverse. It's a plus b times a squared minus ab plus b squared. So those are things that are useful to memorize. Let's start by factoring a polynomial. This is a trinomial. We can use the reverse box strategy. So we'll start with our box, and then we multiply those two terms together, and we think what times what equals -15x to the fourth. And I know I have to have one positive and one negative, but they have to add together to equal the middle term. This is not going to work, neither is this. But I have a feeling one of these two will work, so let's look closely. This is the group that also adds together to equal -2x squared. So I put those two terms in any order along the diagonal. And now you just factor out of the top row. The common factor is x squared, and you fill out the rest of the box from there. X squared times what is x to the fourth? X squared times what is -5x squared? X squared times 3 is 3x squared, and check your constant terms. They definitely multiply together to equal -15. So my factors are across the top and down the side. X squared minus 5 times x squared plus 3. And that does not factor any further. Here's another example that we can use the reverse box strategy for. This is a real nice one because we have all positive terms. So when I go to find the factors of 45 that also add together to equal 14, it comes up right away. Put those right along the diagonal. Factor out of the top row an x squared, and then just continue from there. And I'm done with that one. That does not factor further. A lot of people want to say that x squared plus 9 factors. It does not. That's the That is not the difference of perfect squares. Be careful there. So that's fully factored. All right, now here's one where the leading coefficient is not 1. So this is pretty challenging when you don't use the box strategy. Therefore, let's use the box. Let's multiply those two together, and we get 40x squared. We start listing factors of 40x squared. And we stop when we see the one that also adds together to equal the negative 13x. So I found it. So those go along the diagonal. Now out of the top, this time, we can factor out a 2x. 2x times x is 2x squared. 2x times negative 4 is negative 8x. X times negative 5 is negative 5x. So now along the top, we have x minus 4. Along the side, we have 2x minus 5. All right. Factoring using the reverse box strategy again. 8x to the fourth goes in the top left. Negative 3 goes in the bottom right. Multiply them together, you get negative 24x to the fourth. Our two factors are negative 8x squared and 3x squared. But that doesn't add together to equal positive 10, does it? That doesn't add together to equal positive 10 either. But this group does. So I can write those along the diagonal in any order, factoring 2x squared out of the top. We're left with 4x squared. 2x squared times negative 1 is negative 2x squared. 4x squared times 3 is 12x squared. And 3 times negative 1 is negative 3. So now when I factor my original trinomial, I have 4x squared minus 1 times 2x squared minus 3. But I'm remembering that that one is the difference of perfect squares. It can be factored again into 2x minus 1 times 2x plus 1. And don't forget to bring down the other binomial factor. So hopefully this stuff is coming back to you. Now we're going to factor this polynomial. We're going to do it by grouping, and you're going to see this beautiful flexibility of the box model because I'm putting my x to the sixth in the top left. I'm putting my negative 32 in the bottom right, and then I'm writing the other two remaining factors along the diagonal. I typically just put that one there because it came first and put the other one there. Now out of the top row, we can factor out x to the fourth. X to the fourth times x squared is x to the sixth. Isn't this lovely? X to the fourth times 2 is 2x to the fourth. X squared times negative 16 is negative 16x squared. So my first round of factoring looks like this. I do see that the second binomial is the difference of perfect squares, so I can factor it into x squared minus 4 times x squared plus 4. Now the x squared minus 4 is again the difference of two perfect squares. That factors into x plus 2 times x minus 2. So my original polynomial with 4 terms is factored as x squared plus 2 times x squared plus 4 times x plus 2 times x minus 4. All right, so we're getting the hang of this factoring by grouping because we're going to try this again. Negative x to the sixth goes in the top right, and negative x cubed goes in the bottom left. What comes out of the top row? What's the biggest factor they both have in common? That's x to the sixth. By the way, you always want to factor out a positive right there if at all possible. It's just a little bit better. Now x to the sixth times x cubed is x to the ninth. Along the top goes a negative 1. Along the side goes negative 1. So I'm ready to write my first factored form of this polynomial. I do see that the second binomial is the difference of perfect squares because x to the sixth is a perfect square. X to any even power is a perfect square, and 1 is a perfect square. Now I see x cubed minus 1. I see it 2 times over. That's the difference of perfect cubes. So you can look back at the previous slide and we reviewed what that formula was. Now the only thing I would recommend at this point is just putting your linear factors first, then your quadratic factor, then your cubic factor. And that is a review of factoring.